Okay, first let me thank very much Marcello and Chiara for organizing this wonderful conference and for your very kind invitation. And I wish I could be there in person, but anyway, so are things. So let me start actually, Giuliola just made my first slide like very easy. So I'm going to be talking about the periodic nonlinear Schrodinger equation with power nonlinearities. The power P is always going to be odd in what I'm going to say. And as you know, we have the Hamiltonian conservation and mass conservation. And the sign is only going to matter when I say something about the global dynamics, in which case we will take it to be defocusing. And so the first thing that I want to recall is that these equations have a scaling in the Sobolev scale, which is d over 2 minus 2 or p minus 1. And so the local in time well-posedness for the NLS on the torus says that if your critical index is bigger or equal than 0, and you take data in HS with s bigger than the critical, strictly bigger than the critical, then it follows from the Strickhardt estimates, like as Giuliola says, that you have local well-posedness. And as Giuliola also said, if you take S to be the critical and to be 0, so when you are in the L2 critical, for example, the cubic NLS in 2D, then actually the local well-posedness, just the local well-posedness is actually unknown. And we just saw that Giuliola has some progress in this direction, very interesting. Now, the other thing is that if S is strictly less than the critical index, then we know that this is what we call the supercritical regime, that some ill-posedness may occur. So the purpose of this talk is to take a different point of view and ask, what happens generically? That means instead of individual solutions, what we are interested in is in the family of solutions that are distributed according to some canonical law, like the Gaussian law, or they could have in which we randomize the coefficients, the Fourier coefficients, or it could be we could take the uniform distribution on the unit circle, which amounts to sort of randomizing the phases, and so either one is fine, and they're both equivalent. And so the G's here are IID complex Gaussian random variables that are centered and normalized. So formally, the law for this F is given by the Gaussian measure, which I say formally because, of course, this is abstract nonsense. This should be understood as the limit of finite dimensional approximations. So the d rho is the Gaussian measure that is the exponential of the H alpha norm to square times the Lebesgue measure. And what I want you to remember is that alpha here, which is the power here, is always at S plus the dimension over 2. And if you take that alpha, then this function F is always going to belong to HS minus. So it's going to be below HS for any, so it's going to be HS minus epsilon for any epsilon. And the reason is because that's the support of this measure. I mean, in order to make this measure to be countably additive, there is a trace theorem that tells you that then this measure should be supported in HS minus. So remember these two numbers. And so by switching to an almost sure point of view, what we can say is that we can actually cross this scaling barrier and get almost sure local well-posedness. That means almost sure strong solutions for values which are supercritical. That means for values which are S relative to the critical scaling. And historically, people only know weak solutions in this supercritical case with no uniqueness. And we know very little about that in the deterministic sense. So, but in 1996, Bourgain, in some seminal paper, showed that if we consider canonical random data, so I'll just show you, in some deterministically supercritical space, HS below the critical scaling, then almost surely you can get global solutions. Okay, and this was a total shift or paradigm shift in the point of view of in dispersive PD. And so a key point of this is that if you have random initial data and you combine, then you can actually combine that with sort of large deviation estimates and other type of random matrix estimates, to produce better linear and nonlinear estimates than those for arbitrary functions of the same regularity. So what are the fundamental questions? So despite actually, there was a lot of work after Bourgain, so there was a big gap between 1996 and essentially 2007 in which nothing much happened, but then there was an explosion in 2007 and there was a lot of work done in this sort of like a context. But despite numerous follow-up works of Bourgain, they remain these fundamental questions that I'm interested in, or we are interested in, which is, what is this optimal value S? I mean, how low can you go and still obtain almost sure local well-posedness? I mean, which is because in some sense, these follow-up works, what they did is they sort of like said, well, you can go a little bit below the critical, but you know, it was never optimal. So what is this optimal S? And more importantly is this fundamental question of how does given initial random data gets transported under the NLS flow. In other words, if I give you initially something that is Gaussian, how this Gaussianity propagate? I mean, and more precisely is, can you tell me or can you give me, at least for a short time, a description of the solution beyond the linear evolution? Okay, so you know that the linear evolution of random data, you know it, but then you have no other information. You had no other information about the random structure of that term. And so why this is important? Well, these questions are important in many topics, like, for example, when you study the invariance of Gibbs measures, and this is something that lies sort of very nicely in the intersection of PDE and statistical physics. And here I want to point to some papers that I put in the footnote, which are actually very nice and very important. And it's also very important, as we will see in the next talk by Saher, in the weak or wave turbulence context. So let me talk a little bit about invariant Gibbs measures. So when you're talking about invariant Gibbs measures, then the typical element in support of the measure looks like this, when alpha is exactly 1. So every time that you talk about Gibbs measures, you take random data with alpha being 1. And what happens is that if you're in one dimension, this object is a function. But if you're in higher dimensions, like 2 or 3, then this object is a distribution, and it gets rougher and rougher as you increase the dimension. So in dimension 2, this object belongs to a Sobolev space that lives below L2, to H0 minus. That means that you are below L2. And if you're in 3 dimensions, it's even worse. It belongs to H minus a half minus, which is even rougher. And this is actually a big problem if you want to prove any sort of well-posedness result. And so from the Hamiltonian structure of NLS, you know that the Hamiltonian is conserved. So you could formally write the Gibbs measure as the exponential of the Hamiltonian times the Lebesgue measure, or as the exponential of the potential energy times the Gaussian measure corresponding to alpha equals to 1. And this is formal because, of course, everything that I'm writing here is infinity, right? I mean, it sort of doesn't make any sense for you in these spaces. And you cannot define this, but you understand this as weak limits of finite dimensional approximations. And the construction of these measures actually could be rigorously justified as weighted Gaussian measures, like, you know, like you could justify this to be the Radon-Nikodym derivative of the mu over d rho 1. Actually, this was a big field, and a lot of work was done about this construction and the properties and the various dynamics in the context of statistical mechanics, quantum quantum field theory, constructive quantum field theory, and this is related to the so-called phi4 model when p is 3. So the construction actually can be done in dimensions 1 and 2 for any p. And in that case, the measure, the Gibbs measure, is absolutely continuous with respect to the Gaussian measure. But in dimensions 3, the construction can only be done for p equals to 3 and no other p. And actually, the measure that you obtain, the Gibbs measure that you obtain, is not absolutely continuous with respect to the Gaussian measure. Okay, and there is actually recent work by Barashkov and Guinelli, which gives a better understanding of what's going on here. And there was also an unwritten proof an unpublished proof by Martin Hare on this. But this is actually one issue. And if the dimension is bigger or equal than 4, then the construction cannot be done by NEP. And there is recent work, very nice, by Einsmann and Duminel-Coppen in this direction. And so how about the invariance of the measure together? I mean, the invariance in the strong sense in which you want to get invariance, but so in order to get invariance, you need a global solution. But what you want is to construct not weak solutions, but you want to construct global strong solutions on the statistical ensemble of the measure, and then obtain invariance. And actually, sort of the key question here, you could construct weak solution, global weak solutions. So the key question here is a question of uniqueness. And so formally, this measure can be seen invariant under the flow because the Hamiltonian is conserved and you have Gibbs theorem. But the point is how to make it formal. So the difficulty, as I said before, is that the Gibbs measure is supported in very rough spaces, H1 minus D over 2 minus, when the dimension is bigger or equal than 2. So if you want to study the dynamics, you need to take data which are distributions in these very rough spaces and try to find a solution. And so one thing that you should bear in mind is that unlike something like the stochastic Higgs equations or the wave equations, the Schrödinger semigroup has no smoothing whatsoever. There is no gain of regularity. It doesn't buy you any gain of regularity. So how are you going to do that? Can you see my screen? Because I got some.
Yes.
Can you see my screen? Because I got a message that says participants can now see your screen. So I thought that nobody saw anything until now.
Oh, no, everything is fine. Just go on.
Okay. So the invariance of this measure was actually justified, dimensions 1 for any P odd by Bourgain in 1994. And in dimensions 2 was only justified for P equals to 3. Remember, the construction can be done for any odd P. By a fantastic paper, a seminal paper of Bourgain in 1996. And so the question is, what happens in dimensions 2 for other P that are odd, like P equals to 5? And so this was an open question since 1996 until 2019, in which together with Yu Deng and Heiti and Yue, and I forgot to say that everything I'm saying is a collaborative work with Yu Deng and Heiti and Yue, who was a former student of mine. We solved this question, and then we actually proved the invariance of the Gibbs measure and the almost sure existence of strong solutions, that means the uniqueness of the NLS in the two-dimensional tori for any power, any odd power. So we can actually complete the full picture in dimensions 2. So the only remaining problem is what happens with the cubic in dimensions 3. And this is still an open problem, and it's very hard. But the question actually that is intriguing, the tantalizing question is why? Why is it so hard? Okay, so up to now, it's like you say, why is it so hard? I mean, if you look at this problem, then the deterministic, the critical scaling is 1/2. But if you look at the dimension 2 and the quintic, then the critical scaling is also 1/2. So why is it that this is so much harder than this? They both have the same critical scaling, which is H1/2. And so we answer this question by finding the optimal value, by finding, or actually in our paper on the 2D Gibbs measure, we actually define or come up with this probabilistic scaling definition. We say that the optimal value is the right way of looking at this problem is not through the deterministic scaling, but through the probabilistic scaling. So we define the critical index in probabilistic scaling to be -1 over P minus 1 as the threshold for NLS with random data. And heuristically, this number is based on the basic idea that comes from the central limit theorem that you have a square root cancellation of sums of independent random variables. And so what we prove is actually that this is indeed optimal in the sense that first we obtain local in time strong solutions in the full subcritical regime relative to this probabilistic scaling. And this should be compared with the work of Merton-Herring, which he also, using regularity structures, was able to prove the full subcritical regime relative to the parabolic scaling, which is -2 over p minus 1. So here we do the same thing in the context of the dispersive PDE, which is harder, as I said, because the Schrodinger semigroup buys you no smoothing, while the heat semigroup buys you 2 derivatives. And moreover, what we do is we give a precise description of the solutions in terms of multilinear Gaussian. So in other words, we answer these questions of how does an initial random data, something that looks Gaussian, how does it propagate under the NLS flow, and how does it look like? Okay, so we can actually tell you exactly for short times, how does it look beyond the linear evolution? What is it that you see? Okay, and I'm going to show you a little bit later. So the second result is the one that I just said, which is the invariance of the Gibbs measure. So in the 2-dimensional tori. And the key point, actually, the reason, which is answering the question that I just said as to why this problem can be solved, is because if you actually look at the probabilistic scaling instead of the deterministic scaling, then this problem, the 2-dimensional Gibbs measure problem for any odd power p bigger or equal than 5 is always subcritical. Why? Because the Gibbs measure is supported just below L2. So the S where you're trying to solve the problem is 0 minus epsilon, it's minus epsilon. But the probabilistic scaling is always -1 over p minus 1, which is always below minus epsilon. So you're always subcritical relative to this scaling, and this is why this problem had a sort of a chance of being solved. And we also prove more recently a third result, which is that we improve Bourgain's result on the 3D Hartree NLS Gibbs measure. And I will say more about this at the end. Okay, so sorry about the noise, but it's kind of like I hear a lot of noise from the traffic here. Okay, so what is it? So we obtained these 3 results. And so let me actually, first of all, explain you heuristically, how did we come up with this probabilistic scaling? So what is it that happens? So suppose that I take a very simple initial data, something that is homogeneous. So you take a data which is of a single frequency, n to the minus alpha, and this is kind of like a uniformly distributed on the sort of a sphere of radius n or on the ball of radius n. So this data is bounded and has unit size in HS, where S is as before. Okay. Now, if you want a local well-Posner's result, then what should happen is that when you consider the iterations, then you should stay in HS. So if I look at the second iteration of this initial data, so you have the linear evolution of this, and the second iteration will be U1, which is the Duhamel of putting, say, the linear evolution of this function in the nonlinearity. And so what you expect is this to be bounded in HS for every fixed time. So let's fix a time of, say, order 1. And let's say that k is still like of order n. And let's calculate the Fourier coefficient of this U1. So if you calculate it, then you get that the Fourier coefficient in space is n to the minus p alpha times the sum, right? You have a convolution here. So you take the Fourier transforms, you will have here the corresponding algebraic equation from the convolution, that is k1 minus k2. Remember that these are complex solutions. So you have u times u bar times u bar, blah, blah, blah. So you have k1 minus k2 plus k3. So the minus is because of the bar. And then you have 1 over Japanese bracket of omega. Omega is the resonant factor coming from the linear evolutions times your random variables. Okay, So for simplicity, I'm going to take this resonant factor to be 0. So here, this will be exactly 1. So then this expression is going to look like, this expression is going to be n to the minus p alpha times the sum over k1 minus k2, blah, blah, blah. Kj's of order n, and omega 0 means that you just have this. And so I'm going to assume, and you will see later that this is actually reasonable because of some renormalizations, that these remain independent. So K1 is not equal to K2. So every time that you have a bar and a non-bar, they're all different. Okay, so you have here, so that these remain independent. And so this leads exactly to the square root gain cancellation, because if you take the absolute value of U1, then you get n to the minus p alpha. And by using sort of a large deviation and dimension counting, you get that this is controlled by the cardinality of this set to the 1/2. If you didn't have these random variables, if you had just one, then this will be just 1, and then you will not have these two. And that's what gives the deterministic scaling. But here you have this 1/2. And so if you want this to be bounded in H-test, you get that this is bounded in H-S if and only if minus P plus P, D minus D minus 2 divided by 2 plus S plus D over 2 is negative. And this implies that S has to be bigger than minus 1 over P minus 1. And this is what gives rise to the probabilistic scaling. So let me give you a picture of what's going on a little bit. So let me call the probabilistic scaling minus 1 over P is this magenta color. The support of the Gibbs measure is always just below this number, which is 1 minus D over 2. So the support is in SG minus. And the green is the critical index. So if you're in dimensions 2 and P equals 3, then the probabilistic scaling is minus 1/2. And what Bourgain was looking at a problem in which he was taking random data here in the blue thing, and in order to solve his problem, he had to produce some sort of regularity smoothing to be able to gain enough regularity to be a bubble 2. Okay, so he had to move epsilon and be able to be a bubble 2 to solve his problem. In the case in which you have a P which is 5 or bigger, the situation is much more dire because, okay, the SPR is still below the support of the measure in the quintic is minus 1/4. But now you don't have to gain epsilon regularity in order to solve your problem. You have to actually be able to go from here to above 1/2. So you have to produce from nothing some sort of like smoothing of regularity, which is bigger than 1/2. And if P is large, it just gets worse. And so why is it that 3 dimensions and qubit is harder? Because what happens is that when the P is 3 and dimension is 3, the probabilistic scaling, okay, and the SG are exactly equal. So they become, these two numbers become equal. So that's what we call probabilistically critical. So in all these 3 pictures, the problems are probabilistically subcritical because you are above SP, but here things flip. Then the SG minus becomes below, and these 2 numbers are the same. So this problem is what we call probabilistically critical, while the 2 dimensions is probabilistically subcritical. So our main result actually is the one about the local well-posedness. Says that if P is odd and you are above for the full range of the probabilistically subcritical, then under a suitable renormalization of the nonlinearity, and for the data that I show you, alpha random data, then almost surely there exists a strong local solution that is unique in some suitable sense. And furthermore, and this is actually quite beautiful, this solution has an explicit expansion in terms of multilinear Gaussians with what we call adapted random tensor coefficients that actually localize like Fourier multipliers. So in some sense, I will show you later that there is quite an explicit expansion, and you know exactly how the solution looks like, how this random Gaussian data has looks like for later times. And so deterministically, what was known is this green portion. And so what this theorem does, it proves you all this pink portion. it tells you that almost surely you have local wave bonds everywhere here. And so, and Bourgain was actually somewhere here. So Bourgain went from in p equals to 3, the S critical, this number is 0, and so he was just below here. So the renormalization that we need is actually the weak ordering renormalization. And this is because an infinite L2 mass, that's what we have in the support of the measure, implies that the potential energy is almost surely infinite. And so the nonlinearity doesn't make any sense as almost surely as a distribution. And so this infinity is removed by doing this weak reordering, which is a renormalization. And when I said uniqueness in a suitable sense, what I mean is that our solution is the unique limit for all possible canonical approximations of regularizations of the equation. And as I said, we barely miss this because this is critical and we are probabilistically subcritical. Okay, so the second result is a long time result. And actually, this comes from the proof of the previous results. So it's a consequence of the proof of the previous results. So it comes a little bit in the wash and concerns what we call well-prepared smooth data, such as that arising in the derivation of the wave kinetic equation in wave turbulence. And so this is a long time existence result. And what it predicts is the time of the first energy cascade, which is consistent with the wave turbulence theory and is expected to be sharp. So what it says is that if you take data of a single frequency and Fourier modes, which are sort of uniformly distributed in the ball of radius k less or equal than n, then with high probability, there is no energy cascade between the Fourier modes up to a time that looks like n to the p-1 times s minus, and here is the big thing, minus the probabilistic scaling. So this number, s minus SPR, is much, much larger than s minus the critical one, okay? So this is much longer. And what I would like to point out is two things. One is that here, this is for NLS. We don't need the weak ordering. And this is because the worst contributions that can only be rescued by weak ordering come from the high-low interactions when the high frequencies form a pairing and produce a mass term. But when you are with homogeneous data, there is no difference between high frequencies and low frequencies, so this is not an issue. There is no need to renormalize. And the second point that I want to make is that here we are working with the square torus. So the solution to this problem for long times is actually dominated by exact resonances. But if instead of using a square torus, you would be working with a generic irrational tori, then you would expect this time to be much larger. You would expect conjecturally here to have a 2 times p-1 times this, which after rescaling is equivalent to justifying the wave kinetic equation up to the kinetic time scale in wave turbulence, which is exactly what Zachar is going to tell us about in the next talk. Okay, so the third result, which actually came before the other two, is exactly the result that tells us that if we are in 2 dimensions for any p odd, we indeed have global strong solutions almost surely. That means for any data in the statistical ensemble of the measure, and we have the invariance of the Gibbs measure. And so here is a picture. The green is what Bourgain had done, and somehow the pink is what this result is achieving. Okay, so in other words, we have to cover all of this. Okay, so let me explain you a little bit about how Bourgain proved his results so that I can tell you a little bit more about the new methods that we need to introduce to solve all these problems. So what is it that Bourgain did? So of course, Bourgain also considered the weak order NLS, and I put quotation marks because it's not written like this. You have to go through finite dimensional approximations, put the expectation, blah, blah, blah. Let's just pretend that it looks like this. This is a cubic nonlinearity. And as always, when you're doing something with this measure, the data has alpha equals to 1. And this function, or the support of the measure, is just below L2. So it's in H minus epsilon. So thus this problem is deterministically supercritical because you are below L2, but you are probabilistically subcritical, right? As we said before, as I show you with the lines. And so how did Bourgain solve this problem? Well, what he did is he did what we call the main idea was to make a linear, nonlinear decomposition, where the linear part is rough and random, okay? And the nonlinear part, he proves it to be smoother. So what he did is he constructed this sort of, you should think of this as an affine way of writing the solution, in which it's sort of, this is centered here, and this is in a ball, which is in a smoother space. And so he constructed solutions of this form and showed that the V actually is better than L2. So this is rougher below L2, but this is actually in some HS with S bigger than L2. And the way that he did this is by considering the equation for difference equation, okay, which is written here, where now the nonlinearity is going to have the interactions between the rough and random part and the deterministic part. So he has to analyze all possible interactions between random with themselves, and deterministic with themselves, and then random, deterministic, and so on. And the way that he achieves this is by using sort of multilinear large deviation estimates, analytic number theory. He has to do some integer lattice counting estimates. And then there is something crucial in this problem that differentiates this from the wave equation. So in the wave equation, you can actually solve this problem and you can get away only with the first 2 points because the wave equations has 1 degree of smoothing. But when you have no gain of regularity whatsoever, as is with the Schrodinger, the right way of exploiting randomness is actually to do these star arguments that Bourgain does, which actually are nothing but some random matrix estimates, okay? And this is a very, very important idea. I'll come back to that later. So what is the problem with the 2D Gibbs and P bigger or equal than 3? Why is it that we cannot do what Bourgain does? Okay, so if you consider P equals to 5 and say, and then the criticality, the deterministically is 1/2, and suppose that you were to follow Bourgain and do the linear decomposition, then this will be below L2. And as Bourgain showed, the best you can do for B is to put it in, say, H1/2 minus, okay? But H1/2 minus is still supercritical relative to this. Okay, so you cannot close these estimates by themselves because you don't have enough regularity. You need to be above 1/2. Okay, remember our first theorem. So, but what is actually happening here that you can prove is that this poor regularity in the V comes only from the high-low frequency interactions. So what you can do is you can try to identify from V, you can try to peel off from V these bad high-low interactions and identify them. And so you identify the term X from V, which is para-controlled by the linear evolution of random data, which essentially means that this X is the Duhamel of a para-product between the linear evolution, the high frequencies of the linear evolution, and the low frequencies of the P-1 powers of P. This is just the weak ordering, plus a smooth term. And you want to hope that X, or you want to prove that this X behaves like the linear evolution of random data, and that if you peel off this X from V, then actually the term that you're going to get is in fact smooth enough so that you can actually close then by a fixed point argument. So in some sense, you would like to say that if you peel from V this X, and instead of having U linear plus V, you have something like U linear plus X plus V, then that you're plus some W, then you're fine and you can close. Now, what's the problem? The problem is that to justify this, okay, you need to have some information about the low frequency components. This is a paraproduct, so you have the low frequency components of u to the p minus 1. But the up minus 1 contains x. So in order to understand or to have some information on the low frequency components of up minus 1, actually, you need to have some information about the x to the p minus 1. But the regularity of the xp minus 1 is still h half minus, which is still supercritical. So there is no way of using just the regularity to control this term. So doing this, you cannot just put this in a function space and say I'm done and do this decomposition that I told you between the linear x plus w. If you were in heat or in the wave, you can. And this is what the paracontrol calculus does, because the gain of regularity tells you that this x is in a much better space than this. It's in a smoother space, so you can directly put this term in a good function space and be done. So the question is, how do we do this? Okay, so how do we tackle this? And in order to tackle this, we need to know more than just the regularity of this term. Okay, we need to really understand the random structure of this term, of these low frequency terms. Okay, so we need to unveil and invoke the structure of x. So how can we do this? So the point is that in order to justify the behavior of x, we need to justify the behavior of x. And the way to do this is by induction on frequency and justify the behavior of the lower frequency parts of x before you can justify the high frequencies part of x. And so for simplicity, forget the paraproduct and suppose that at frequency n, this is the little Bailey projection of frequencies n, you have the sum of all the frequencies that are much smaller than n and the high frequencies. So this is high frequencies, low frequencies. And so in order to do what I just said, you could say, well, I'm going to do a recursive reduction, and I'm going to say, well, I'm going to write the low frequencies of x in terms and sort of I'm going to take this, I'm going to iterate and write them in terms of even lower frequencies of x, of lower frequencies r, of below L, and so on until I reach frequency 1. So you can do some reductive reduction and go from L all the way to 1 by iteration. But the problem that this iteration gives you a very complicated and tricks function that involves all frequencies, all scales from n to 1, which are very hard to treat simultaneously. And the amount of combinatorics is completely out of control, is overwhelming. And you could try to do this for p equals to 5, but we want to do it for all p. And so we seek a different method than this. And we actually do we change our point of view. So this is what I call a paradigm shift. So the goal here is to capture the implicit randomness structure of this x term that contains the low frequency parts of the solution in some norm or quantity that propagates. What I mean by that is that if you can prove the estimates for the low frequencies, if you have some induction, then you can prove them for the high frequencies, okay? And so clearly the norm h half minus is not going to work because it's a supercritical norm. So in order to understand this, we really need to change the point of view. And instead of viewing this as a function that we want to place it in a function space, we take this term, right? And we change the point of view. We view it as an operator, okay, that maps y into the Duhamel of p and y times this term, okay? So instead of actually viewing this as a function and placing it in function space, we think of this as an operator. And so this operator depends on the implicit random structure of this term. And it basically has the structure of a paraproduct. So you could think of this as a projection onto frequency n, followed by a weighted average over the smaller scales. And you could think of this that this is being applied to the Gaussian free field. And this is the reason why we call this a random averaging operator, which is just a random matrix operator, and is the key to propagate the right probabilistic bounds. So what are these bounds or these norms that we use? And this is actually the beautiful part because they're very easy to manipulate. So in order to propagate the right norms, is this, we need to prove these two a priori estimates, which are this PNL is an operator that is a linear operator between two Hilbert spaces. So one is this is the operator norm from L2 into L2 or from some Fourier restriction space to itself. And the other one is simply the Hilbert-Schmidt norm. So this a priori estimate tells you that this term is in h½ minus, which it keeps it there as you propagate, which we cannot use directly. But this is the norm that actually allows us to propagate. Okay, so this is the key norm. And so this is all we need. We need some operator norm and some Hilbert-Schmidt norm. And so if you had actually general functions in h½ minus, if instead of having these, you have general functions, you have no prayer of proving these two a priori estimates. So really this random averaging operator captures the randomness structure of the low part. And actually these are very easy and tractable to use. So in order to give you the right answer for how we solve this problem, instead of a linear nonlinear decomposition of Bourgain, let me actually change a little bit the point of view and think of the random averaging operators as matrix, random matrices, or what I call 1-1 tensors. So for the pictures, instead of P5, I take P equals to 3. So the blue ball is the linear evolution of the random data localized to frequency n, and the light ball is just the low frequency part of the solution. So this picture means that you have exactly the Duhamel of the cubic term with the linear and the low, okay? And then you iterate, right? So in the first entry, you put this and you keep iterating and so on. And if you do that, and you sum all these trees, you get the linear evolution plus all these iterations. And let me call that this cube, blue cube. I'm going to call it psi n and delta. So n delta is your low frequency, your L. So to sum all of this is equivalent to find this psi, which is to sum all of this, is equivalent to solve this paralinearized equation, which is essentially the linear evolution of U plus this random averaging operator NL, here L is n delta, applied to the psi itself, right? Because this is exactly the Duhamel of the cubic term with psi in the first entry and U and delta in the other two. So essentially what we are saying is that this cube, this psi, is simply the linear evolution of random data plus this configuration where here, instead of having the linear evolution of data, you have psi itself. And if you solve that, then what it tells you, you can solve it explicitly, is that this psi is nothing but the sum over n, okay, of all the PNLs. So the sum over L of all the PNLs that I showed before applied to the linear evolution, okay? And so this is your random averaging operator. And if you sum, so if you take the Fourier transform, what you have is the linear operator is simply this, what is this linear operator is doing is actually giving you a twist of your initial Gaussian random initial data. Okay, so this matrix is a random tensor matrix, and is going to be independent, is random, and is going to be independent of this Gaussian. So these two things are going to be independent, and it's something that is absolutely crucial that we keep. So to understand the ansatz, so what we do is we write U as the sum over n of this psi, which is simply the linear evolution plus the sum over n of these configurations, plus a remainder, which is the same as U linear, the linear evolution of random, plus the sum over n of this. Plus a remainder, and actually, so this linear evolution of random is in a space, is where your data is, which is below L2. This term is going to be, as I told you a minute ago, in h½ minus, and the remainder is actually be very smooth and very nice. It's going to be almost in H1. So once you peel off from the remainder, okay, this term, then you can actually solve for this via fixed point argument like Bourgain does. But you need to actually identify and peel off this term from here, which comes from this understanding of the high-low interactions and this point of view of viewing this as an operator rather than as a term. So if you expand this in Fourier series, then the Fourier coefficient of this function looks like this, which comes from the linear evolution, your random averaging operator, and the remainder. And so this is, as I said before, the random matrix. And this random matrix actually, is there a question?
No.
Okay.
There was no.
Okay, so this random matrix actually carries all the random information of the low frequency components of the solution that we were talking about before. So, okay, so that's what we use in order to solve the 2D Gibbs measure problem and this answer. Now we want to solve the first theorem, which gives us the full local wave constant in the full subcritical regime. We actually need to do a much more sophisticated theory whose cornerstone is this answer, these 1-1 tensors. But it's a theory that we call the theory of random tensors. Okay, so let me focus about how do we prove these local wave constant in the full subcritical regime relative to the probabilistic scaling. Theorem 2, as I said, follows from theorem 1, and this random average operators is actually a first step or the cornerstone of this random tensor theory, and actually is enough to treat many problems to treat many problems where you are far away from the probabilistic scaling. So for theorem 1, what we need is higher order expansions than the first one. So right, the linear random average operator is linear. So we have to do higher order expansions, which actually lead to multilinear expressions, which actually is what we call the Q1 tensors. And D here is the order of the expansion, is some fixed number, which can be arbitrary. So we can expand up to arbitrary order. And these are the tensors like before depend on the low frequency components of the solution. So let me still take P equals to 3. And so our answer now on the Fourier side is that what we seek is to write our solution so that the Fourier coefficients can be understood as a sum over Q. Q is less or equal than D, which is the order of the expansion. And you have the sum of, you have this tensor, these coefficient tensors, which actually depend on, they are sort of independent from these Gaussians. They're random and independent from these Gaussians, plus these multilinear Gaussian expansions. So now you have, you don't have just a Gaussian, you have the tensor of 2 Gaussians, 3 Gaussians, and so on as you go. So you have a precise description of the solution, plus a smooth remainder, and this remainder gets smoother the longer, the higher the D. Okay, so plus minus means bar no bar, and what you want to achieve in your ansatz is that there are no pairings in here, so that these always remain independent. And if the size of kj is nj, and you call capital N the maximum of all these frequencies, then you also want to achieve that all these nj's are bigger than, say, some low frequency, which is where you stop the iteration, which is n delta. So then all these functions are going to depend on the Gaussians, on the random variables that correspond to k, which is less than n delta, while these are above n delta. So they are going to be independent. And so these quantities, where T is the view as a parameter, are what we call the random tensors and are the main subject of study. And the convergence of these, so the point is, how do you prove how do you converge? How do you prove that this series converges? And for that, you need to study these objects and prove some estimates on these tensors. And as I said, these come from these high order iteration trees. So I have some examples. Let me just show you quickly one. So for example, what is a 2-1 tensor? The 2 refers to the fact that you have 2 linear evolutions of random data here and a low one, right? So that's the 2. And the 1 is the k, which is the output, okay? So in here, what as I said, this n1 and 2 is bigger than n2 delta. So if you take the Fourier transform, which is what I did before of this thing, what you get is exactly the sum over K1, K2 of this object. So this is a low frequency, and this is your random tensor view as a function of the variables K1, K2 into K, and then you have the product of two Gaussians. So this will be the 2-1 tensor. Okay. And there is, of course, a lot of different configurations for 2-1 tensor. Here I have one that is more complicated, but okay, let me skip this. So the random tensors framework allow us to get a handle actually on this exploding complexity that arises from these higher order iteration trees. This is actually a theory that gives us a way of controlling this. And for that, we have to develop an algebraic theory, which focuses on the structure of the tensors and how these tensors are built from smaller tensors using operations such as tensor products and contractions. And it gives rise to two operations which are key, which is the merging of tensors, which is how you go from small tensors to bigger tensors, and trimming, which is something a little bit more technical, which is actually needed in order to keep the independence between the tensors and the random variables. And we, of course, need to develop the analytic theory. In other words, we need to develop suitable norms for these tensors, as we did before, which actually propagate so that we can do an induction in frequency argument. And these norms, this analytic theory has to respect the algebraic theory, has to respect these operations of merging and trimming. So the merging simply says, like, if you have, like, say, these three tensors, and suppose that there is no pairing, so none of these frequencies are the same, then what you get is a new tensor, which is a 6-1 tensor, which is written here. And this base tensor is an explicit tensor, which is not random and comes from the nonlinearity, but this is exactly just a tensor product and gives you a 6 tensor. Now, if you had a pairing, so suppose that this frequency is equal to this, remember that here you have a bar. So if this frequency is equal to this one, then in order to get a 6-1 tensor, what you get is a 4-1 tensor by contracting. You have to contract over repeated indexes. So if A is the same as B, right, then you need to contract over repeated indexes, and instead of 6-1 tensor, you get a 4-1 tensor. And trimming, as I said, is something technical, which is that in all these operations of merging and trimming, sometimes you fall below the end delta that ensures the independence. So you need to trim it. And the way that you do that is by contracting against the Gaussians here, so that this new tensor is indeed independent with the Gaussians ABC. Okay. Okay, so this is a little technical, so doesn't matter. So the analytic theory, again, as before, is based on very easy norms, which is, again, the operator norms and the Hilbert-Schmidt norms. And now we have much more variables. So the tensors can be viewed as mappings from functions of part of the variables, and you have a lot of flexibility which part of the variables you choose into some other set. So you can divide K1, so K into K, so you can divide this any way you want. And so, for example, here you have HK, X, Z, Y, and here you have a choice of an L2 norm, and that's what it is. And sometimes you just sum over all of them, you sum over the Hilbert-Schmidt, okay? And so we prove two estimates. One is for merged tensors, which says that if you have a tensor that came from merging these three tensors, then say, for example, the L2 norm as from functions from BZ into C omega is bounded by the product of these three L2 norms. And one thing that is important here is that this is just an example, because the order in which you put these tensors here is free. You can order these tensors any way you want, but the order in which you have here is fixed. So that means that for any order here, you get a different estimate. That means that, in fact, what we get is a lot of flexibility. We get a set of multilinear estimates, and we have freedom to choose the best ones each time. And then we have actually what we call a trimming estimate, which is a random matrix estimate, which actually is one of the most important estimates in the whole paper. which essentially says that if you have a tensor that came, say, from contracting against Gaussian, this tensor is independent of this. And then the L2 norm of this from kx into z, for example. So n here is the maximum of all the frequencies. So up to an epsilon loss here, this is bounded by the maximum of all possible multilinear estimates that you can choose here, okay? So the proof of this goes back to what I told you before, Bourgain, which relies on high order TT star arguments and multilinear estimates. And even in the simplest cases, this seems non-trivial to prove. And we think that this estimate, which is very elegant, has some sort of independent interest in the study of random matrices with Gaussian entries. So once we have the analytic and the algebraic theory at hand, we can conclude, because what we want is to prove this, we want to prove these bounds for these tensors so that we can sum this series. And so this nj to the beta, beta is smaller than alpha. So this nj to the beta growth are killed by the decay here. And so this maximum nj to the minus beta is the decay that allows you to sum, okay? And so, moreover, we also prove that these tensors satisfy sort of a weighted estimate that tells you that in the support of these tensors, then they're essentially localized on some diagonal hyperplane. So what that tells you is that in the Fourier expansion, you have linear evolution of random, and as you go, then you have something that is an almost diagonal matrix times a Gaussian. Then you have something that is almost diagonal against the tensor of 2 Gaussians, then something almost diagonal tensor of 3 Gaussians, and so on. So it's a very delicate and very precise description. And what I would like to say here is that this should be seen as the analog of the random tensor theory should be seen as the analog of the regularity structure theory for parabolic singular stochastic PDE. In that case, somehow what is done because of the heat kernel is localizing. The expansion is a Taylor series expansion that is localized in space, and it also involves multilinear Gaussians, while in our case, the expansion is done or involves is performed on the Fourier side. So let me actually, I know that I'm actually getting close to time, but I'm going to take a few minutes to finish this and tell you something very, very interesting, which is about the Hartree and the Gibbs for the NLS. So in here, we are going to take we are in 3D instead of 2D, and we are going to take the Hartree equation with a potential that is essentially a Bessel potential, okay? So it's real, even, and we are going to think of this being defocusing. So essentially just a potential of this form. And the scaling of this equation, the deterministic, is 1 minus beta over 2. And I should say that if instead of NLS, we take nonlinear waves, there has been recent work of Brinkman and Okamoto Ptolemaev in this case. And so what we prove is that if beta is below 1, okay, so if beta is below 1, so here the Fourier coefficients of B decay like 1 over k to the beta. So, but if you take beta below 1, beta less than 1, but close to 1, then we actually can prove the invariance of the Gibbs measure and the existence of global strong solutions. So Bourgain in his paper had proved that if beta is strictly bigger than 2, you can prove this theorem. And essentially what we can say is that if we are below 1, we can also prove this theorem. And we can actually prove this theorem using, again, just the random averaging operators, because we are subcritical. In this case, we are still subcritical. For any beta bigger than 0, this problem is subcritical. And we think that you can go all the way to 0 if, if instead of random the average operators, you do the sort of the Hartree adapted random tensors theory, then you could actually go all the way to 0. And then if beta is 0, then you have no potential, then this is critical and becomes a 3D NLS, okay? So what I want to tell you is that the answer here is a little bit different than from the 2D NLS because there is in the nonlinear NLS, what did we do in 2D? We have the linear evolution, random averaging operators. In that case, this was in H0 minus, this was in H1/2 minus, and this was in H1. Now we are in 3D. So this is in H minus 1/2 minus, this is below L2. And the problem is that the remainder has a piece which behaves like a probabilistically critical term. Okay, and so what we have to do is we have to modify the answer here, and we have to add, so besides the random averaging operator, we have to also add a modified random averaging operator, which intuitively you could think of that as being solving this equation. I just want to have one more slide. I'm finishing soon. And the problem is that this term exhibits a probabilistic critical behavior. And so you need to remove it from here. And the reason is because you see, if the frequencies, so if the output of this is frequency 1, then this V is irrelevant. So this essentially will behave like the cubic equation, okay? And so if it behaves like the cubic equation, then if you think, or if you want to put this term in the remainder, the problem is that you lose a little derivative. If W is in HS, then this term is not going to be in HS. It's going to be in HS minus epsilon. So you cannot close. It's going to lose regularity. So you need to separate. And this term also, you cannot view it as a random averaging operator because it has a different structure, but also because if W is in HS, the random averaging operator of W is in HS, so this is a term in the remainder and this isn't, okay? So this is actually a beautiful problem because actually for the first time, we see this probabilistically critical component showing its head in the remainder, and it needs this modification to solve this problem. And in this, I will stop. Thank you very much.
Thanks for the talk. Is there any question or comment? Well, I can see here as well as online. Oh, Benjamin.
Maybe I'll ask one.
Yeah, I think you have to speak loud. I don't know.
Can you hear me?
Yes.
Yeah. So you were on the torus, right? Do you know if this kind of probabilistic approach can also be used on the full space? Has it been used already?
Yeah.
Or?
Yeah, we get this question all the time. It can certainly be developed in the full space, and even in the random theory. There has been a lot of work done in the wave equation by Luhrmann and Mendelssohn, and also O and somebody else. I can't remember the names. I'm sorry, I blanked out with the authors. In which what you do is you have to do a different randomization. Of course, you do this sort of like Wiener randomization, in which you sort of randomize the projections into Fourier squares of size 1, and then you can actually do it in RD. And so definitely you can develop all of this theory in RD, and that's a very interesting question. Actually, it's a nice problem, but it hasn't been done, and it's certainly worth doing.
Thanks. Maybe I have a question. It's a little bit vague. I mean, it seems that you do a little bit as if the renormalized NLS and the original NLS are a bit the same. But to me,
can you say?
Yeah.
Can you say it? Can you put a little louder?
Yes. Okay. Let me try to speak louder. So NLS has to be renormalized, right?
Yeah. Yes.
And it seems that in your mind, this renormalization makes the renormalized NLS very similar to the original NLS. But to me, they look completely different in general. So
no,
I mean,
no, I'm not saying that they. I'm not saying that they are the same. I'm just saying that this is the construct, even the construction of the measures and are done for the weak order NLS, not
yes.
for NLS.
So
even in Bourgain's case. Yeah.
Exactly, but when you think of S as a parameter, somehow you always think of the true NLS as belonging to the same family as the renormalized NLS. For cubic, I see it's reasonable because somehow the only thing we do is to add a very fast phase or something by changing chemical potential. But If I look at the quintic, for instance, then definitely renormalization adds a cubic term. So isn't renormalized quintic, isn't that closer to the cubic quintic NLS in spirit?
In terms of the, you're talking about the deterministic scaling. I mean, our point here is essentially that somehow viewing these random data problems, or any way you want, through the lens of the deterministic scaling, any deterministic scaling you want. I mean, I just wrote the one for the pure power nonlinearity for simplicity. It's actually the wrong lens because it's not the right scaling for these random data problems. But the right scaling is this probabilistic scaling, and that probabilistic scaling, and we actually prove that it's the right one and it's the optimal.
Okay. Any other? No questions. So thanks again, Andrea.
Thank you.